Hello everyone, I welcome you all to the course of heat transfer. Today's session we will discuss another important topic, that is convection. As you all know, convection is a process of energy transport affected by the circulation or mixing of a fluid medium. It is possible only in the fluid medium and is directly linked with the transport medium itself. There are two ways of convective heat transfer. First one is natural convection. Another is a forced convection. The name itself indicates, in case of forced convection, the heat transfer is supported by external agent like pump, blower, fan, etc. Whereas in case of natural convection, the transport phenomena occurs because of change in density. These are the examples of forced convection as well as natural convection. Again, there are categories. We can have external flow as well as internal flow. Now, flow over this can be considered as forced convection provided the flow of fluid is supported by an external agent. For example, a blower in this case. Now, this is an example for internal flow where the flow is occurring inside the pipe or a tube. And again, the cold fluid is passed with the aid of an external agent. In this case, it could be a pump if we consider the cold fluid to be a water. Similarly, this is an external flow where the cold air is entering at the bottom of the solar collector, and when it leaves, it has gained heat. And once the air collects heat, obviously the density of air will goes down and it will move up. Similar is the case with respect to the chimneys. This is categorized under internal flow, where the flow will be occurring inside the structure. Generally, the structure of chimneys is made such that naturally it will support the flow based on variation in density. Now, we all know the convective heat transfer is governed by the law of Newton's law of cooling, wherein Q convected is equals to change in temperature divided by convective resistance. The convective resistance is 1 over HA, where H is the heat transfer coefficient and A is the surface area. We all know convection is a surface phenomenon. And Tw and T infinity are the wall temperature or surface temperature, and fluid temperature respectively. As we discussed, the flow could be external flow, wherein the flow engulfs the body with which it interacts thermally. In case of internal flow, the heat surface surrounds the surrounds and guides the convective stream. In forced convection, there will be an external source. As discussed, it could be a pump or compressor or a fan or blower. Whereas in case of natural convection, it is initiated by the change in the density of the fluids. And there could be a mixed convection, which is a combined form of forced as well as natural convection. And these are some of the processes and the corresponding heat transfer or the convective heat transfer coefficient values. In case of natural convection, for gases, the value of H varies from 3 to 20 watt per meter square Kelvin, whereas for water or liquid under natural convection, the value of H varies from 60 to 900 watt per meter square Kelvin. Now, if you consider a forced convection, you can see there is an external agent schematically shown here. Now, for a same surface area and for a same heat transfer, for same surface area as well as for same temperature difference, if you consider, for gases, the value of H is ranging from 30 to 300, whereas for oils it is 60 to 1800, and for water it is 100 to 1500 watt per meter square Kelvin. Obviously, in case of forced convection, as the value of H is more, the amount of heat transfer will also be more for the same temperature difference and surface area for a given case. The value of H for boiling and condensation is even higher. It varies from few thousands to 1 lakh. It could be 3,000 to 1 lakh. Now we will come across some dimensionless group which are used to identify the processes. The first dimensionless group, it is given by a name Prandtl number. Prandtl number can be defined as the ratio of momentum diffusion to the heat diffusion or thermal diffusion. Momentum diffusion is also called as viscosity diffusion to the thermal diffusion. Prandtl number can be less than 1 or it can be greater than 1. It varies between 0 to infinity. The second dimensionless number is Reynolds number, which is defined as the ratio of inertia force to viscous force. And if you deduce the equation for Reynolds number, it is rho VL upon mu or rho L upon mu, where mu is the kinematic viscosity, mu is the dynamic viscosity. Mu by rho gives you the kinematic viscosity mu. Similarly, the Prandtl number is given by mu Cp by K. This kinematic viscosity can be written as mu by rho, and alpha can be written as K by rho C. Now, if you deduce the equation, Prandtl number can be written as mu C upon K. The next dimensionless number is being Becklet number, which is a product of Reynolds number and Prandtl number. This is generally used in forced convection. The next dimensionless number is being Grashof number, which is defined as the ratio of buoyant force to viscous force. Grashof number generally will be used in natural convection, and if you take the product of Grashof number and Prandtl number, it will yield another dimensionless number, which is a Rayleigh number. A Rayleigh number is given by the product of Grashof number and the Prandtl number to some powers multiplied with some constant. Next is a Nusselt number. As you all know, Nusselt number can be defined as the ratio of convective heat transfer to the conductive heat transfer, or it is also defined as conductive resistance to convective resistance. Next is the Stanton number, which is a function of Nusselt number and Becklet number. The Stanton number can be written as Nusselt number upon Becklet number, where Becklet number is the product of Reynolds number and Prandtl number. In case of equations that you come across in order to find the Nusselt number, the Nusselt number will be of this form. Nusselt number will be some constant into the product of Grashof number and Prandtl number to some powers. Nusselt number can be equated to HL upon K, where K is the thermal conductivity of the fluid. Now you will have Nusselt number value out of empirical relation, which is obtained from heat transfer data handbook. And if you equate that with the value of HL upon K, you will get the value of H. In this topic, the major numericals will involve the calculation of heat transfer coefficient for different conditions. It could be internal flow, it could be external flow, it could be laminar, it could be turbulent. So based on that, you need to first calculate the value of Nusselt number using empirical relations. Then you need to calculate the value of heat transfer coefficient using the relation Nusselt number is equals to HL upon K. Now, another important concept is being the boundary layer. The formation of boundary layer is a very important concept. Now, essentially, a boundary layer will form when you have a flowing fluid over a surface. Now, in this condition, let us consider a flat plate over which air is flowing with a velocity of u infinity. Let u infinity be the mainstream velocity. Now, this point is termed as leading edge, and this point is termed as trailing edge. Now, if we consider the length of the plate to be L, now at x equals to 0, the flow is initiated. At this point, when air is flowing and when it passes over the plate, the air layer which is adjacent to the plate will loses its velocity, and the velocity at this point, which is very near to the surface, will be 0. And this condition is also termed as no slip condition, where there will not be any relative velocity between the fluid as well as the surface. Now, once the fluid reduces the velocity to 0, the next upper layer of the fluid will also get influenced by this. As a result, the velocity of the upper layer of the fluid will also reduces. It will not be 0, but it is not as same as mainstream velocity. Now, this first layer will induce resistance to the flow of the next upper layer. As a result, the velocity of the second layer will also reduces. Because of the viscous effect, that will in turn reduces the velocity of the next upper layer or the third layer. So this process goes on because of the viscous effect. As we have considered the flowing fluid to be a real fluid. A real fluid is a one which will have viscosity. And all of you know viscosity is a property wherein it will offer resistance to the flow of fluids. Now this point is at rest because of the contact with the stationary surface. So this induces a resistance to the next upper layer of the fluid. As a result, the velocity will come down. This will in turn reduces the velocity of the second upper layer. As a result, the velocity of this will also come down. Now, as we move from the top surface of the plate, the velocity goes on decreases up to a certain point, after which the velocity will be as same as the mainstream velocity. Now, if you take the vertical distance up to which you can see the viscous effect, that vertical distance is called as boundary layer thickness. In other words, it can also be defined as this is the distance where you get the velocity which is equals to 99% of the mainstream velocity. It means to say that in the boundary layer you will have viscous effect. Now, once you cross this limit, the viscous effect will not be there on the fluid. Hence, the velocity of the fluid will be as same as the mainstream velocity. Now, if you consider the curve form, it will have a parabolic nature. Now, if you ask the value of hydrodynamic boundary layer thickness at point x equals to, say, this is 0.1, 0.2, 0.3, the value of hydrodynamic boundary layer thickness goes on increasing with the length of the plate. Now, this is nothing but the velocity profile, which is parabolic in nature. Now, if you see, the boundary layer thickness at point 1 is less than the boundary layer thickness at point 2, which is less than the boundary layer thickness at point 3. Now, if you join all the boundary layer thickness at point 1, 2, and 3, you will have this curve, which is the extreme curve of the boundary layer, above which the fluid is independent of the viscous effect, and below which the fluid will be affected by the viscous effects. Again, we can have three different regions. One is a laminar region, transition region, and turbulent region. As you all know, the laminar flow or the turbulent flow is determined using a dimensionless number, that is Reynolds number. The Reynolds number for flat plate, to consider it to be laminar flow, it is 5 into 10 to the power 5. If the Reynolds number is less than 5 into 10 to the power 5, for flat plate, we can consider it to be a laminar. If it is greater than 5 into 10 to the power 5, then it will be turbulent. And the critical Reynolds number is having the value of 5 into 10 to the power 5. If it is below, that is laminar. If it is above, the critical Reynolds number, that is turbulent. It is not same for all conditions. The critical Reynolds number is 5 into 10 to the power 5 only for flat plate, that too external flow. And in a similar way, for pipe, the Reynolds number, if it is 2300, then it is considered to be laminar flow. If it is between 2300 to 4000, it is considered to be transition. And if it is more than 4000, it is turbulent. Similar is the case with open channel. Now, if we calculate the value of Reynolds number, if the Reynolds number is less than 500, then it is laminar. If it is between 500 to 1000, then it is transition. If it is more than 1000, it will be considered as turbulent flow for open channel. For different flows, the Reynolds number will be different. It is not same for all the cases. This should be considered. And Reynolds number is given by V into X upon mu, where u infinity is the velocity, X could be any distance. It could be L by 2, it could be L, it could be L by 4, and mu is the kinematic viscosity. You can also have a form of rho V into X upon mu, where mu is the dynamic viscosity. This is the diagram wherein the velocity profile for hydrodynamic boundary layer as well as the temperature distribution for thermal boundary layer is given. I can see here the point very adjacent to the plate is having zero velocity. As we move up, the velocity goes on increases. At some point, the velocity will be equals to the mean stream velocity u infinity. Now, within the boundary layer, the velocity will be less than that of the mean stream velocity. Similar is the case for temperature distribution. Again, the temperature or the thermal boundary layer can be defined as it is the vertical distance where we can find the temperature equivalent to 99% of the initial temperature or the initial fluid temperature. Now, if you see here, the temperature very adjacent to the plate, even though there is flow of fluid, the fluid will catch more heat. Hence, the difference in temperature will be more. As we move upward, the difference in temperature goes on reducing because the air which is flowing at certain distance from the plate will absorb less energy. As a result, if you take the temperature difference of this with the temperature of the fluid, that will come down. Similarly, as you move upward, at certain point, there will not be any temperature difference between the fluid and the temperature of the fluid which is flowing above the boundary layer. Now that vertical distance measured from the surface of the plate is considered to be thermal boundary layer thickness. In this case, we have two cases, one with a Prandtl number greater than 1, another with a Prandtl number less than 1. Prandtl number can also be defined as the ratio of velocity boundary layer to the thermal boundary layer. It is the ratio of delta upon delta t. Now, if delta is more, the Prandtl number will be more. If delta is less than delta t, the Prandtl number will be less than 1, because the numerator is less than the denominator. Here, in this case, you will get a value which is less than 1. Sometimes it could be equals to 1, where delta is equals to delta t. In your problems, for a given hydrodynamic boundary layer thickness, you may be asked to calculate the thermal boundary layer thickness for a given Prandtl number. Generally, this kind of questions will be asked in competitive exams. Yeah, as I told, the velocity boundary layer is that vertical distance where you get 99% of the mainstream velocity. Similar is the case with thermal boundary layer. The temperature distribution should be 99%. Next, if you consider the value of H, it is calculated as per unit area. If you take H is nothing but, this is the Fourier law of heat conduction per unit area, and this is the temperature difference between the fluid as well as the surface. If you take the ratio, you will have the value of H. Then the average heat transfer coefficient along the length is nothing but the integration of H with respect to the length Now we have discussed the empirical relations for Nusselt number, which is a local Nusselt number is some constant and the product of Reynolds number and Prandtl number to some powers. These are some empirical relations that you can find in heat transfer data handbook. The local value of Nusselt number under laminar condition over a flat plate is given by 0.332 Reynolds number to the power 1 by 2 into Prandtl number to the power 1 by 3. So I'll give you the reference. This is in page number 113 in 8th edition of Heat and Mass Transfer Data Handbook. Now this is nothing but uniform wall temperature. You can also have uniform heat flux. The average Nusselt number is given by 0.664 RE to the power 0.5 into Prandtl number to the power 0.33. This is for fluids which are having Prandtl number greater than 0.6. Similarly, for liquids, the Nusselt number is given as 0.565 to Re to the power 0.5 and Prandtl number to the power 0.5. So again, this is appeared in page number 113 of your heat and mass transfer data handbook. Similar is a case for turbulent boundary layer. As I told, for flat plates, we will consider the flow to be turbulent if the Reynolds number is greater than 5 into 10 to the power 5. These are some empirical relations wherein you can use the values of Reynolds number and Prandtl number and calculate the value of Nusselt number. And if you use that Nusselt number, using that, if you put in this value, HL upon K, you can have the value of heat transfer coefficient. Using that, you can also calculate the amount of heat transfer using Newton's law of cooling. This is an internal flow where the flow will be inside the tubes or pipes. This is the velocity profile. You can see at this point the fluid is in contact with the inner surface of the pipe where the velocity is 0. This is again a no slip condition and the velocity is maximum at the center. The velocity can also be calculated using a standard relation m dot is equals to rho v into a, where v can be calculated as m dot upon rho into a. So a is nothing but pi by 4 d square for a pipe, where d is the diameter of the pipe. The Reynolds number is nothing but ud upon mu or rho vd upon mu. So in this case, this is kinematic viscosity. If I consider kinematic viscosity as mu upon rho, so rho vd upon mu will be there, where mu is the dynamic viscosity. We have seen the Reynolds number for pipe flow. If it is less than 2300, it is laminar. If it is between 2300 to 4000, it is transition. If it is more than 4000, it is turbulent. The hydrodynamic boundary layer thickness can be calculated as phi x, where x is the length at which you need to calculate the boundary layer. X could be L by 2. If the length is L, it could be L by 4 upon square root of Reynolds number. Similar is the case with thermal boundary layer. Now you can again use these empirical relations for laminar flow as well as turbulent flow. Now for pipes, for uniform wall temperature, Nusselt number is given as 3.66. Similarly, for uniform heat flux or uniform wall flux, the Nusselt number is given as a value of 4.36. You can have these values in page number 128. I'm giving you the reference. It is different for different profile. For example, for ellipse, for constant wall temperature, it is 4.439, whereas for constant heat flux, it is 5.331. For a square cross section under constant wall temperature, it is 2.976, and for constant heat flux, it is 3.60. In this way, the value of Nusselt number varies depending upon the profile, and these two values are for circular profile or circular cross section. Similarly, you can have triangular cross section, hexagonal cross section, rectangular cross section. For different cross sections, you will have different value of Nusselt number for uniform wall temperature as well as uniform heat flux. Now, if you consider the tubes, the internal flow, you have the Nusselt number empirical relation is given by Dickers and Boelter. It is given by Nusselt number is equals to 0.023 Re to the power 0.8 into Prandtl number to the power n, where n is equals to 0.4 for heating of the fluids and is equals to n is equals to 0.3 for cooling of the fluids. And generally, you will collect the properties at the mean fluid temperature. Now, if you consider the flow over the cylinder or sphere, it will give you an idea about attached flow as well as detached flow. If the flow is laminar, it will wrap around the sphere or cylinder. If it is turbulent, it will detach the surface much earlier. So as a result, you will have a separated flow which will create the formation of wake, and it will increase the adverse pressure. As a result, the drag coefficient will increase. In order to avoid this, we need to have a streamlined bodies as shown in this figure. You can see all along the surface of the fluid, all along the surface, the fluid is making an attached flow. This could also be the reason nowadays all the vehicles, automobile vehicles, are having a streamlined bodies in order to reduce the drag coefficient. The drag force is given by CD into AN into rho V square upon 2. That CD is the drag coefficient. The AN is the frontal area. This gives you a clear idea about the nature of the surface. If the surface is smooth, it will create a thick wake which will increase the drag coefficient, and if the surface is not smooth, it will reduce the formation of wake. So this is essentially, you are making the flow to be turbulent if you allow more disturbance on the surface of the golf ball. So it will create the flow to be turbulent even at lower velocity. So this will reduce the wake. This will reduce the drag coefficient. These kind of questions can be asked in competitive exams. You need to understand the concept behind this. With this, I'll stop here. Thank you.